Thank you very much. Let me start with a picture. So I would like to talk about p-adic versions of BSD and the conjectures of Birch, Smith, and Dyer connect two faraway mathematical worlds together in the context of an elliptic curve. So let E be an elliptic curve over Q. And associated to this elliptic curve, and more with its rational points, one can associate various invariants on the analytic side and on the algebraic side. So for example, on the analytic side, one is interested in the behavior of its L function, or L functions of E, p-adic or complex. And then on the algebraic side, one is interested what one is interested in, or what one can associate, is one can work with cohomology. Inside cohomology, there's a very interesting group called SHA, the Tate-Average group. I did it again. SHA. I always write the character for mountain. Anyway, it's a SHA. We don't know if it's finite, for example. And one algebraic invariant, for example, is this R, the rank. And fortunately, the conjecture of Birch, Smith, and Dyer conjecturally connects these two worlds together, which are far away. By looking at the situation in the context of the light of the Archimedean prime. So let me denote this by infinity. If you shine the light Archimedean prime on this, one gets this connection. But there are more subtle connections that one can discover by shining the much weaker light of the prime numbers on it. So because the light of the prime number 2 or 3 are five and p in general p. And these connections only appear when one is willing to ignore some of the features that are intrinsic to the light of complex analysis, or the Archimedean prime. So let me state the conjecture of Birch, Smith, and Dyer in this context. So classical BSD asks if the order of vanishing of the L function at a special value is equal to the rank. And once we've written this out as a nice power series, we're interested in the leading term. We denote this by L star. And this should be proportional to the size of SHA. Assuming it's finite. Now, p-adic BSD is a very similar statement, but for that, we first need to come up with a nice p-adic avatar of the L function. So the thing to do is the following. Do I need all this? So look at an extension of Q whose Galois group is isomorphic to ZP, the p-adic integers. This ring can be realized as an inverse limit of Z mod p to the nz, which are the intermediate fields sitting inside Q infinity. A p-adic L function is usually a function sitting inside a group ring, completed group ring like this. With this CP is the CP here, the Galois group. We can think of this as sitting inside a power series ring of one variable. So now one has a nice p-adically analytic object. And p-adic BSD typically asks if the order of vanishing of at a special value is equal to the rank, and whether again, the leading term LP star is proportional to the size of SHA. One advantage of this p-adic version is that it behaves well in families. So you can say something about what happens for each of these Qn sitting inside the cyclotomic tower. So the conjecture doesn't really end here. You can also ask if you take a primitive p to the nth root of unity, what's the order of vanishing at zeta p to the n minus 1? And here the conjecture typically asks whether this is equal to the jump in the rank of the Qn rational points of the elliptic curve. Well, whether it's proportional to that. So the rank is the phi part of this group of rational points of the elliptic curve as an abelian group. And this part is a little bit more subtle. So let's assume that LP does not vanish at zeta p to the n minus 1. Then, so this is true for sufficiently large n. One may then ask if this is proportional to something very similar to this thing. The jump in the p primary size of the Tate-Jaffa-Hurwitz group as one goes from level n minus 1 to level n. All right, so what can we say about this? Well, let's focus on this quantity. It should be equal to something like p to the en minus 1. And we can estimate this quantity en minus 1 analytically, just conjecturally, and see what happens. Oh, I can run this board too. Awesome. So So let me sketch a theorem. For this theorem, I need to introduce this quantity here, a sub p, which is the difference in the expected number of fp rational points of the elliptic curve and the actual number. And let me call v the p-adic valuation of this number a sub p. So here's a sketch of a theorem. So in the case where v is equal to 0, this follows from the methods of Maser, and v is equal to infinity, this follows from the methods of Robert-Pollack. And it can also be done in the other cases. So if you choose v somewhere between 0 and infinity, you can think of a sub p sitting inside the unit p-adic disk. So for example, if you're in the middle of the unit p-adic disk, then a sub p is equal to 0. So the p-adic valuation is equal to infinity. Or you can be on the outer edge, in which case the valuation is equal to 0. Now, on the outer edge, Maser has given a nice formula for this quantity, for this e sub n minus e sub n minus 1. And the formula here is of this form. It's of this form. Mu times some normalization coefficient plus lambda, where mu and lambda are algebraic invariants or analytic invariants of the elliptic curve. Let's call them Iwasawa invariants. In the so for a long time, it was not really clear what to do when v is greater than 0. But about 10 years ago, Robert-Pollack discovered that in the case v equal to infinity, there's a pair of formulas that describes this phenomenon quite nicely. These formulas look very similar, but they involve a pair of invariants. So these qn flat and qn sharp are explicit p-power sums. But the pair of invariants comes in for odd n and even n. So they take turns in determining the expected growth of SHA. Now, here's a crazy phenomenon that goes on in between. So look at the circle, the boundary of the disk where v is equal to 1 over 2p. And construct appropriate objects so that you can extract the pairs of invariants, mu sharp, lambda sharp, and mu flat, lambda flat, and build a tube of radius which is equal to the difference between these mu invariants. Around this circle here. When v is inside here, then, so let's, with a loss of generality, let's assume that mu sharp is less than mu flat. Then inside here, for some reason, the formula only involves one invariant, one pair Iwasawa invariance, mu sharp and mu flat. So in this case, the growth of SHA looks a little bit like the ordinary case in that there are no pairs of invariants that appear, but it also looks a little bit like the supersingular case in the case where v is greater than 0, because there's this p power sum in here. And furthermore, if you're inside this disk here, then you always have this growth property. Right, so this is the case for elliptic curves. For elliptic curves, v can only be 0 in infinity or 1. So depending on whether 1 lives inside the orange region or this region close to the origin, you may have different formulas for the growth of SHA, these towers of number fields. There are generalizations of this theorem to modular forms where some crazy phenomena go on the boundary, in the region between this orange annulus and the outer edge. But I won't have time to sketch that, so let me finish here.
Thank you very much.